Here in our own cosmic backyard, we've uncovered a tremendous amount of information about the universe, discovering many fantastic facts and properties about reality that our long-ago ancestors could scarcely fathom. We now know that planets form in a wide variety of masses and sizes, from sub-Mercury-sized planets all the way up to super-Jupiters, with smaller planets being more common, but harder to detect, than their more massive counterparts. Planets can form at all distances from all different types of stars, with rocky planets being quite common around nearly all types of stars. However, many generations of stars needed to form, live, and die previously to make the formation of rocky planets possible, as the universe started off with only hydrogen and helium as raw ingredients. But rocky planets are primarily composed of heavier elements, the elements forged inside stars themselves. As we close in on 6,000 confirmed exoplanets, and as astronomers and astrophysicists prepare to design and build the first space telescope capable of directly imaging Earth-sized planets at Earth-like distances around Sun-like stars, we're becoming more and more capable of searching for signs of life beyond Earth. But without a second example of life, there are many burning questions that remain unanswered. Here are some of the biggest ones. 1. Did life on Earth actually originate on Earth? This might seem like a no-brainer, as it's easy to assume that Earth-based life, because it's found only on Earth and not any place else we've ever looked so far, is unique to our planet itself. But this isn't necessarily the case. One can imagine a number of possibilities for how Earth life arose. Life originated on Earth once and has survived ever since to the present day. Life originated on Earth many times over, and all of those instances, lineages except one, went extinct at various points, leaving only evidence from the one surviving thread for us to observe. Life originated elsewhere in the universe, either in interplanetary, interstellar space, or on an entirely different world, and came to Earth long ago, seeding our planet with life that happened to find conditions under which it could survive and thrive. All of these are within the realm of possibility, of course, as the only evidence we have is the presence and record of life on Earth encoded within our own planet, and the lack of signs of life, either related to or independent of Earth life, elsewhere within our solar system and our universe. Mars, the Moon, Venus, plus moons like Titan, Triton, Ganymede, Europa, Enceladus, as well as dwarf planets like Eris, Pluto, and Ceres are all candidate worlds for either past or present life. But thus far, no compelling, incontrovertible evidence of biological activity has been found on any world other than Earth. This evidence, however, doesn't tell us which of the scenarios concerning the origin of life on Earth are most likely. We know there are complex organic molecules found all throughout interstellar and interplanetary space, including in star-forming nebulae, in protoplanetary disks around newly forming stars, and in outflows from massive young stars. We know that if we look at the asteroids and on other worlds found in our own solar system, there are even more complex organic molecules that are quite common. Sugars, amino acids, nucleobases, and many other molecules that are seen as precursors to life. But in order for life to actually emerge, we need more than even these complex molecules. We need something that can metabolize a source of energy, for example from nutrients, from sunlight, starlight, or elsewhere from the environment, and use that energy to conduct life processes, and also that can reproduce itself and give rise to a subsequent generation of offspring. All forms of life that exist on Earth have these two things in common, including organisms like viruses that are sometimes classified as living, and sometimes as non-living, depending on what criteria are used for defining life. Whether Earth-based life originated on Earth or elsewhere in the universe is still an open question. 2. How common is life of any type throughout the universe? One of the best analogies I ever heard concerning the question of life in the universe is that of a lottery. Each world that forms around each star, whether it's a planet, moon, or dwarf planet, is like a lottery ticket. All of a sudden, a huge number of questions arise. Will life ever form, arrive at, and take hold on this world? If life ever does arise, will it go extinct relatively quickly, or will it survive for long periods of time? Will there be multiple independent origins of life, or just one if life does arise? And if that life does survive and thrive for long periods of time, what will be the most complex, differentiated, intelligent, and/or technologically advanced form of life that it becomes? Even that first question of whether life ever forms, arrives on, or takes hold on such a world is something whose frequency we have no idea about. Here on Earth, all we know is that life came to exist on it somehow, at some point long ago, as far back as the fossil records can take us, and possibly even earlier than that. But on all other known worlds, from exoplanets to the planets, moons, and dwarf planets in our solar system, we have no signatures of life anywhere. If life in the universe is a cosmic lottery, then we have a serious set of unknowns to reckon with. What are the minimal sets of ingredients and/or conditions that we need to have a non-zero chance of life coming into existence on such a world? Is water required, and if so, how much? Is a parent star required, and if so, what types are permissible? In other words, which worlds are even entrants in such a cosmic lottery and which ones are guaranteed losing tickets? Of the worlds that are true entrants in the lottery, what are the odds of winning any prize? In other words, how likely is life to arise even briefly on such a world? What are the full suite of prizes out there in the universe, from a brief instance of life arising only to swiftly go extinct, to a long, highly diversified, unbroken chain of life, perhaps even leading to intelligent, technologically advanced or spacefaring forms of life? And is life on Earth the grand prize in the lottery, as humans often consider ourselves to be, or is there an even grander prize out there? As is often the case in science, thinking about the currently unanswered questions at the frontiers of our knowledge often leads to a tremendous number of follow-up questions that we'll someday strive to answer as well. At this point in time, however, we don't even know the answer to the most basic question of all: how common is life of any type? 3. How do living organisms first arise from non-living ingredients? Assuming, as scientists often do, that there's no divine intervention in our universe, or that the processes that occur in our universe are purely physical in nature, we're left with the inescapable conclusion that, at some point, something we would consider life arose from what we would consider non-life. A crystal, for example, can reproduce itself, but doesn't have a metabolism, and is considered non-living. Certain classes of molecules, such as enzymes, proteins with ions attached to them, can perform metabolic activities, but don't reproduce themselves, and are considered non-living. And all of the life that we know is far more advanced than a mere metabolic replicator which we can synthesize, like peptide nucleic acids, instead possessing not only metabolisms and the ability to replicate, reproduce themselves, but also contain a genetic string of information that encodes the production of proteins and cell walls/membranes to separate an organism's insides from the external environment. This leaves, as a huge open question, the puzzle of how the life that exists on Earth actually first came into existence from precursor, inorganic ingredients. There are many hypotheses surrounding the origin of life, including origins in interstellar space, hydrothermal vent or hydrothermal field origins, a membrane-first origin, a replication-first origin, a metabolism-first origin, and a nucleic acid-first origin, such as the RNA world hypothesis. Many different groups working on this puzzle favor different sets of origins, as the evidence we've gathered is only circumstantial and indirect. We have not by any means ever synthesized something that we would classify as a living organism from solely non-biological precursor ingredients. Part of the difficulty is that the types of life that survive here on Earth today are already so thoroughly evolved. The oldest fossil evidence of life on Earth comes from approximately 8 billion years ago, but at that epoch, Earth itself was over 700 million years old already. By the time that the Earth was just 1 billion years old, or approximately 5 billion years ago, biologists are certain that life already had developed the ability to transcribe and translate information between DNA, RNA, and proteins, and those mechanisms still exist in every organism that's descended from that long-ago epoch. All forms of life that exist today in fact can be traced back to what's known as LUCA, the last universal common ancestor of life. Unfortunately, that doesn't answer the question of how life actually arose from non-life and what the ultimate origin of Earth life actually was. 4. Which method of searching for life beyond Earth will be successful first? When we talk about looking for life beyond Earth, people normally get one of three pictures in their heads. They think about SETI, or the search for extraterrestrial intelligence, and the possibility of detecting a signal produced by intelligent, technologically advanced aliens that's an unmistakable smoking gun signature of not only their existence and location, but of their eagerness to be contacted by us. They think about journeying to other worlds in our solar system, places like Mars, Venus, Titan, Triton, Enceladus, Europa, Ceres, Ganymede, Pluto, etc., and searching for either past relics of life, examples of dormant life that could be reawakened, or possibly even finding existing simple life. It wouldn't be as remarkable as finding intelligent aliens, but it would teach us our origins are non-unique. Or we could use future generations of telescopes and observatories to build up a suite of evidence supporting the case that a particular exoplanet is actually an inhabited world, containing biosignature molecules and exhibiting the types of changes over time that belie something more than geological, atmospheric, or other inorganic processes that could mimic one particular signature we more typically associate with life. In reality, scientists are pursuing all three of these routes, but arguably the one that gives the best chance of success is the third method. In particular, this motivates the science case for NASA's proposed flagship space telescope known as the Habitable Worlds Observatory. The reason we want to use telescopes is simple. There are more exoplanets out there than there are worlds in our own solar system, and those exoplanets include a large number of worlds that are the best Earth analogs we know of, whereas we have no Earth analog worlds in our own solar system. The SETI method might be appealing, but relies on the assumption that intelligent, technologically advanced life is relatively common. If it is not, and in particular if it's not common right now in our own galaxy, its efforts will not lead to a positive detection. But with space telescopes that can probe the worlds out there in our galaxy and beyond, we can probe the most promising, lottery ticket worlds with sufficient technology. We always strive, from a scientific point of view, to probe the greatest amount of discovery space available with the next generation of instruments that we build. SETI-like efforts would clearly have the greatest payoff but rely on the most generous assumptions about life being true. Probing the worlds in our solar system is fascinating, but the types of life we can find are limited and already highly constrained. We know none of the solar system worlds are teeming with life that transforms the entire planet the way life does here on Earth. But looking beyond, to the great wealth of lottery tickets available in the universe, likely holds our greatest hopes for success. 5. Are we actually unique and alone as a living planet in the universe? Nearly every working scientist in the fields of astronomy, astrophysics, biology, and astrobiology will tell you that the possibility that we truly are alone is a very slim one. There are many reasons to believe that this is true. In every way that we know how to look at the universe, there is nothing about Earth, the solar system, or the galaxy, and our place in it that appears to be special and unique. There are no special conditions or properties that we are known to possess, except for the fact that Earth is a living world, the only one known so far. But that only teaches us we should suspect that we aren't alone. It doesn't allow us to conclude that we have company. If you woke up tomorrow and discovered that everyone around you was dead, everyone in your house, everyone on your street, everyone in your city, etc., what would it take to convince you that you weren't the last living human on Earth? I would argue that you'd need to find a second example of a living person. If there's even one other, there are likely many more. But until you found that second example, you'd have to worry whether you were truly remarkable and unique as the last human on Earth. By the same token, we'd need a second example of life in the universe to know for certain that it wasn't just us. If the 20th century taught us what the universe looked like, the 21st should be the century that sees humanity answer this, and many other, of the biggest questions of all concerning life in the universe. The only question is whether we'll invest in it enough to actually figure out the answers for certain, or whether we'll be left speculating like all prior generations of humans who've pondered the great cosmic unknowns.